Shall I start?
Yes, please go ahead.
Okay. So I'll be talking about bisimulations for neural network reduction. So the broad goal of the work is to investigate foundations for reducing the size of neural networks in such a manner that we can give some formal guarantees between the original system and the reduced system. So the main results go something like this. We define a notion of bisimulation for neural networks such that when we look at the quotient neural networks, they're semantically equivalent to the given neural network. And then we relax the notion of bisimulation to an approximate notion, wherein we don't get semantic equivalence, but some kind of semantic closeness. So let me start with a very brief overview of the syntax and semantics of neural networks, because the whole talk depends on that. And I will motivate this work in the context of safety verification for autonomous systems. All right, so we've all seen it, but here is a quick recap. A neural network consists of a set of neurons or nodes that are arranged in layers. The first layer is the input layer, and the last one is the output layer. And you have multiple hidden layers in the middle. And then there are edges between nodes of consecutive layers, and these edges are weighted. And finally, we have, with each node, a number which is called a bias, as well as an activation function. So I'll get into more details about these. So the semantics of neural networks, the computation of a neural network essentially happens by giving some values to the input layer and propagating those values layer by layer towards the final layer. And the value at a particular node is computed in two steps. The first one consists of a linear transformation, which is essentially a weighted sum of the values of the nodes at the previous layer. For instance, here, the value at the node S11 is going to be the weight on the edge, weight on the two incoming edges, which are multiplied by the values of the corresponding source nodes. That is 1 times 1 plus 4 times 2, and then adding the bias to those products. Okay, so okay, my cursor is not seen here. So essentially, you look at each of the nodes in the previous layer. Here, one of them is marked as S. You look at the value of that node, multiply it with the edge going out of it, and you do that for each of the nodes, add all of those values up, and then add the bias, which is 19 here, which is associated with S11, and that result is the value at the node S11. And the second step is the application of an activation function. One of the simplest ones is called ReLU. If the value is greater than or equal to 0, the value remains the same on application of this ReLU function. And if the value is negative, then it gets truncated to 0. So you apply these linear transformation followed by activation function and get the values at the next layer, and then you propagate this to other layers. So that's how basically neural network semantics works in terms of propagating the values from the input to the output layers. All right, so the context for this work is safety verification of autonomous systems. We are seeing increasing amount of deployment of neural networks in autonomous systems in control, perception, and guidance modules. So here is a very simple example where you have an autonomous car that is controlled by a neural network, and the objective of the controller is to ensure that the vehicle remains on the lane. And so the controller essentially senses the state of the system, which is the position, and then makes some computation and outputs this input U back to which is fed back to the physical system. And the execution of such a closed loop system happens as an alternation between a step of the physical system and a step of the controller. So the controller senses X0 and outputs U0, which is then fed back to the physical system, which then updates its state to X1 and so on. So in order to verify safety of such systems, in this case, to ensure the vehicle remains on the road, we need two primitive computations. One is a post computation through the dynamical system, that is, given a set of values for u, what is the corresponding values for x that would result by going through that physical system. And the second is the output range analysis, wherein given a set of sense states x, we want to output what is the set of inputs that the controller would output. So once we have these two primitive computations, we can iterate over them repeatedly until a fixed point is reached, and that's the read set, which can then be used to verify safety. So we are going to focus on this particular output range analysis, which is the crux to safety verification. So we have this neural network, and the problem that we need to solve is, given a set of initial values, what is the set of values that the output neuron or node would take? Now, a standard approach to sort of compute this output range analysis is to encode the input-output relation of this neural network as a constraint and then solve an optimization problem. So more precisely, let's say you have a variable xs, which represents the value of the node at value of the node s. And you write down a constraint based on these variables, which encodes the input-output relation of the neural network. And then you optimize for you find the max and min values of the variable corresponding to the output neuron. So this approach is sort of used in multiple works, and here is a few examples. Sherlock, which uses an MILP-based encoding, and Reluplex, which uses a satisfiability modulo theory solver. And both of these problems are essentially NP-complete. And so the challenge in verifying these neural networks is, of course, the scalability, because the size of the constraints grows proportional to the number of nodes in the nodes in the system, and the complexity of verification itself could be as bad as exponential in the size of the neural network. So small networks are conducive for automated analysis, no surprise there. And what we explore here is, how do we do this network size reduction? More precisely, we are interested in answering, how can we construct reduced systems that are semantically equivalent in terms of input-output relation, which also guarantees the equivalence of the output range. And our tool is to develop a notion of bisimulation for neural network reduction. So we are all familiar with this concept of bisimulation, which is a notion of equivalence that is used widely in process algebra. And when we take quotients with respect to bisimulation, we get a reduced system which is equivalent to the given system. And we know that bisimulation guarantees global behavioral equivalence by enforcing certain local one-step constraints on the binary relation, which is the bisimulation relation. More precisely, given a binary relation R on the states of a transition system as a bisimulation, if for any two states Q1 and Q2, which are related by that relation R, if one of the states can take a transition, then the other should be able to match it with a transition such that the resulting states are again related by R. Right? So this is the classical notion of bisimulation. Now coming to our neural networks, observe that the value of a node in the neural network depends on depends on the values of the nodes in the previous layer. So our notion of bisimulation is also slightly different in order to enforce the semantic equivalence. And it depends on the notion of, on this operator called the presum. So presum takes as argument two elements. The first one is a set of nodes, and the second one is just a node. And it returns the sum of the weights on the edges from these nodes capital S to the node small s. So here is the graphical representation. So presum of this set of nodes capital S, so sorry, the way I read it is presum of the node S with respect to the set of nodes capital S is the sum of all the weights on the incoming edges from capital S to the small s. Right? So in this case, presum of this S comma S is W1 plus W2 plus W3 plus W4. All right. So once we have this notion of presum, we can now define the notion of bisimulation. So I call it the neural network bisimulation, NN bisimulation. It's an equivalence relation P on the nodes of the neural network. And we will assume that the equivalence relation only partitions nodes, contains nodes from the same layer in any equivalence class. Okay, so neural network bisimulation is an equivalence relation on the nodes such that if two nodes are related, then their activation functions have to match, and the biases associated with the nodes also have to match. And finally, if we look at the presum of the two nodes with respect to any equivalence class capital S, they also need to match. Okay, it seems a little bit restrictive, so I'll come back to that point later in the talk. So what we're saying is if this S and S prime are two equivalence classes, then all the nodes in S need to have the same activation function and bias. So do all the nodes in S prime. In addition, if I look at any two nodes in S prime, let's say the small s and small s prime, then presum of that S and S prime with respect to that equivalence class S also need to match. Okay, so those are the three conditions we have. Okay, so once I have the bisimulation, the notion of bisimulation, I can define quotienting, which is straightforward. So quotienting of n with respect to the equivalence relation P is sort of the standard quotienting. The nodes are the equivalence classes, and the biases and activation functions are pretty straightforward. We associate the bias and activation function of some node in that equivalence class, and it doesn't matter which one we choose because from the definition of bisimulation, we know that they all have the same activation function and bias. So finally, we need to say what is the weight on the edge from, let's say, an equivalence class S to an equivalence class S prime. And we're going to associate the presum of some node in S prime with respect to S as the weight. Again, it doesn't matter which node we choose from S prime because all of the presums are going to be the same according to, based on the definition of the bisimulation. All right. So here is an example of quotienting. So let's say we group together the nodes that are shown in that dotted circle over there. And you can verify that this is an NN bisimulation. For instance, if you look at S21 and look at its presum with respect to the nodes S11 and S12, the value is 4, and it would be the same for S22 as well. Right? And then we can compute this reduced system wherein we represent those dotted group of nodes by a single node, and the edge from S11, S12 to S21, S22 is going to be 4 because that's the presum, let's say, that is associated with S21. Okay, so what do we get from all of this? So for simplicity, we're going to assume that we don't merge any input and output nodes. If you want to know the precise equivalence in that case, you can look at the paper. But for the purpose of the talk, we'll assume that we don't merge the nodes in the input and output layers. So what we get is that if we look at neural network N and look at the quotient of N with respect to an NN bisimulation P, then their input-output relations are exactly the same. Okay, which means that instead of using N in verification, we can replace it with N quotiented with P. So the natural question is, how do we find these P's? Is there a best P? Is there a coarsest P? If so, can we compute, and so on. And it turns out that all of this is true. There is a notion of courses P, and we can use an algorithm very similar to Bisimulation algorithm to find that P. All right, so let me start with some primitives which will help us define this Bisimulation algorithm. The first one is this operation called the split act bias, which given a set of nodes is going to split that set into subgroups such that the nodes in each of the subgroups have the same activation functions and the same biases. So it groups them into maximal sets which have this property. The second one is the notion of an inconsistent pair. So if you have two sets, S and S prime, we say that the pair S and S prime is inconsistent if in S prime we have two nodes whose presums with respect to S are different, right? And if we have an inconsistent pair like that, then we use this function split pre to split S prime based on the presum values. That is, we are going to split S prime into subgroups where each subgroup will have the same presum values with respect to S. Okay, so then here is the Bisimulation algorithm, which might look very familiar to most of you. So the first loop essentially splits the nodes in each. So you start by merging all the nodes in a particular layer. So that's the abstraction you start with. And then you split the nodes in each layer based on activation functions and biases. And then you iteratively find a pair which is inconsistent and split the S prime of that pair using the split pre function until you can no more split. Right? So, what we are guaranteed from the algorithm is that the algorithm always returns the coarsest NN bisimulation. Okay. All right, so here is a quick illustration. In this case, the states S and S prime are inconsistent because if you look at the presum of S21 and S23, they're different. And so you can split them. And then in another iteration, you can split further, and you would end up with this coarsest bisimulation and the corresponding reduced system. All right. So when I started talking about NN bisimulation, you might have wondered that the notion that the biases match exactly and the presums match exactly seemed too restrictive. And yeah, it could happen that if we start looking for exact bisimulation, we might end up with very little reduction. So we relax the notion to something called an approximate and then bisimulation. So the notion of approximate bisimulations have been used in multiple places. In particular, in control theory, these notions have been used to obtain approximately equivalent systems that lead to large amount of reduction. So we define the notion of a delta approximate NN bisimulation, which is again an equivalence relation on the nodes of the neural network. Very similar to what we had before, we still require the activation functions to match. The only change now is that we don't require the biases and presums to be exactly the same, but to be within a delta of each other, where delta is the factor we are using to define our approximate NN bisimulation. Right? So for instance, in this example, if we consider an equivalence relation where we merge S11 and S12, you see that this is not an NN bisimulation because presum with respect to S11 is 0.8, whereas that with respect to 12 is 1. But this is a 0.2 approximate NN bisimulation because the presums differ by at most 0.2. Right? So, and here is another approximate 0.2 approximate NN bisimulation, the one shown in red. But you can see that if I just merge all three of them, that is not going to be a 0.2 NN bisimulation. Right? So already we are heading to the conclusion that there might not be a coarsest NN bisimulation because the union does not satisfy does not preserve the approximate and then bisimulation property. All right, so we can again do a quotient with respect to an approximate and then bisimulation. And the quotienting here is not unique. So broadly, the quotienting is the same as before. You take the equivalence classes as the abstract nodes, and the activation functions of all the elements of a group are the same, so there is no doubt there. But the biases might now be slightly different. So the way we assign a bias to the abstract node is we still just choose one of the elements and look at its bias and associate that. And similarly, for the presum, we just look at one of the nodes in that set and we assign its presum as the edge weight. Right? So now we could result in multiple reduced systems, even for a given n and a p. So here is the example that we had before. So let's say we merge S11 and S12. Then the reduced system could be either of the two. Either of the two. Where in the first we chose to have the weight to be 0.8, whereas in the second we choose the weight to be 1 from S01 to that club node. Okay, so what do we get from all this reduction? It's already clear that we don't get a semantically equivalent system, but we get a system which is semantically close to the original system. So what we in fact get is that, let's say we have n and p is a delta nn bisimulation on n. Then for every uv in the semantics of n, that is given u as an input, v is produced as the output. In the reduced system, we will have an output v prime, which is within some epsilon. And this epsilon is a function of delta, the input, the neural network, and the partition. So I'm not going to write down the expression. You can look at that in the paper again. So we can bound the deviation in the semantics. And so you could still use it effectively to do verification. All right. So that's all I had to say in terms of the results in the paper. So to summarize, we presented a notion of bisimulation for neural networks based on this notion of presum that gives us input-output semantic equivalence. And we can, in fact, use an algorithm similar to Bisimulation Algorithm to find the courses and then bisimulation. And then we looked at the notion of a relaxed notion of approximate bisimulation, wherein we don't get semantic equivalence, but we get this trade-off between how much we want to reduce versus how much deviation we can tolerate from the given system. So going forward, we would like to develop algorithms for, heuristically choosing which of these reduced neural network is better when in the context of approximate bisimulations. And also one thing we haven't done is experimental evaluation of the reduction algorithms, wherein we would like to understand the trade-off between how much reduction we get versus how much precision we lose in the context of approximate bisimulations, and also sort of compare between the approximate versus the exact and see how they fare in some examples. Yeah, so I'll stop here and take some questions. Thanks.
Thank you, Pavithra. There are already 2 questions online. I don't know if you can see them, but Thomas is in the room, so perhaps he could just state the question.
Yes. So we have one question. It appears that the number of layers, so this is a question by Kishore Yosimurugan. The question is, it appears that the number of layers is not reduced using your approach. Have you thought about a potentially more general notion of bisimulation which can achieve reduction in the number of layers?
Yeah, so you're right that, we don't reduce the number of layers, and that might be something interesting to think about. But typically these layers are, the number of neurons in the layers could run up to thousands or millions, whereas the number of layers does not typically run up to that huge number. So reducing the number of neurons in a particular layer certainly seems very crucial there.
Okay, thank you. What about the second question from Thomas?
Yes, I can put this to the back. We have some more questions from the audience. So I'll start
Yeah,
with
please go ahead then.
Yes, I have a question regarding this Presum in the approximate bisimulation. I was wondering, why don't you just take the average Presum? So if you have this 0.8 and 1.0, why don't take 0.9?
You're right. I mean, I think we could take any of them which is within that range, and it would still work.
Okay, thank you.
Very interesting work. I'm curious why you chose bisimulation, not some other equivalence relation like simulation, for example, or any weak notion of bisimulation.
Right. So simulations typically do not give equivalence. They give some notion of an over-approximation. So that's, actually, in fact, I don't know what would be a notion of simulation. It would be interesting to see. And we are looking at one system rather than two systems here. And that's also a reason why defining bisimulations would be more straightforward. Thanks.
Yeah, I had one more question, which was whether you've looked at all into whether there's a notion of a most precise delta approximate bisimulation quotient, maybe by combining the activation functions in some way in the equivalence class.
So most precise delta approximation, right? So certainly there is no coarsest, because to find the core, I mean, the coarsest bisimulation is just the union of all the bisimulations that exist, right? And what we saw here is the union of those two particular bisimulations that I showed certainly is not an approximate bisimulation with the same parameter 0.2. So the notion of coarsest bisimulation certainly doesn't exist. So we might have multiple maximal bisimulations in some sense. Yeah, I mean, that would be an interesting thing to explore, is to see if there is a way to sort of either heuristically or theoretically quantify which one of them might be better.